Here, take
Okay.
take the
I'll take
paper,
the paper.
and then
And the script?
wait.
The script?
Okay, okay, we'll start recording. Okay,
Nice.
so if you take, okay, face there, and so if we drop a rock and a piece of paper, nah, you know you can look here, right?
Oh,
where
yes.
Okay, if we drop a rock and a piece of paper at the first, if we drop a rock and a piece of paper at the same time, which do you think will fall first? Well, if you said the rock, you're correct, because obviously, you know. No, Adrian.
I'm gonna drop it.
No, you're supposed to drop it like this. Like, hold it like
Oh,
this.
yes.
Yeah, there you go.
Okay.
No, at the same, okay,
Same height.
there you go.
Alright. Just drop it so I don't break my feet.
Okay, obviously, the rock dropped first, as you see. But now what happens if we replace that? No, stop. Just stop, dude. Now what happens if we replace this baby with a pencil? 'Cause we don't need that anymore. And it's wet now. That's great. Anyways, now what happens if we replace it with a piece of pencil? Well, according to our previous observation, the lighter object took longer to fall down, and so the rock would have dropped earlier because it was heavier, right? But let's see what actually happens when we drop it. Wow, they dropped at the same time. What a surprise! Huh? No, stop it. That's actually so stupid. Don't ever do that again. Okay. So let's go back inside. We're done with that now.
However, there are times
Are
like
you si-
what?
I'm supposed to come
So-
in with
sorry,
confirmation
please.
bias here.
You- Confirmation.
Can we like?
NANI?!
Alright, considering what you just saw, this misconception we talked about, this misconception commonly arises because of the feather and the heavy object trope in early media. After that, people then concluded that heavier objects fall faster because said heavier object is heavier than the feather. When in most cases, objects of different weight should fall / reach the ground at roughly the same time.
Well, this is mostly due to something people call confirmation bias. I don't know if you've heard of it or not. Confirmation bias is basically where you have your own, where people create their own theory, and they observe the world around them to try and, you know, validate or invalidate their theory. But the crux is that they ignore any sort of evidence that invalidates their theory and only accepts the information that validates their own theory. So, say for example, we have this misconception of the rock, heavy object and the feather trope in real life. So, if we have, for example, this, you'll have to say goodbye. So they'll drop at the same time, basically, because stuff. But we ignore that kind of evidence, and we only accept the evidence that comes from, Tom and Jerry or whatever, where you have that 1,000-ton weight that drops like that, and then you have the feather that goes like that, and then we just come to our own conclusion that, oh, heavier objects fall quicker. And
Well, I agree with you, but there are times like the rock and the paper where one clearly falls faster than the other. This is all due to air resistance, okay? It's all because of air resistance. Air resistance is just basically an object rubbing with air. The larger the surface of the object in the direction the object is traveling, the more air pushes on that object, slowing it down. Air resistance is basically what makes parachutes work, and in this case, is what makes the paper go slower than the rock. There is a large difference in the amount of air resistance the rock has as to the amount of air resistance the paper has. But when we make this air resistance smaller, in the case of the rock and the pencil, which we showed afterwards, the objects will drop at relatively the same time. But why do objects drop at the same time when you ignore air resistance?
Well, the simple answer is mass affects the strength of the gravitational force, but not the acceleration due to gravity. Say we have this is, I guess, some easier way to look at it before we go into our more in-depth explanation. Say we have a 2 over 1, fraction, which is essentially 2. It has the value of 2. If we double both the numerator and the denominator, since they increase at the same rate, this will come into play later on. The result will become 4 divided by 2, or 4 over 2. And 4 divided by 2 is still 2. So the result will still stay the same. This is essentially the same thing as what happens with how fast objects drop in relative to the Earth. So here we can use one of Newton's laws of motion, which is
Mass equals to force times acceleration.
Wait, what
Wait,
did
what?
you just do? oh my.
Force is equal to mass times acceleration.
Okay, thank you. At least, well, whatever. All right. So if we rearrange the equation, so we have acceleration as the subject, because that's what we're trying to get, right? We're determining what happens to the acceleration. So if you rearrange the equation, what do you get?
You got acceleration is equal to force divided by mass.
Exactly. And so if the mass of an object increases, then
the strength of the gravitational force increases as well.
So if both of them increase at the same ratio, then what do you think happens? Just like with the 2 over 1 becoming 4 over 2, if you have force on the top, for example, 2 increase to 4, and if you have mass on the bottom, 1 increases to 2, then it's basically the same thing. Because they both increase at the same ratio and are proportional, then the fraction of the force divided by the mass will stay the same, and therefore acceleration will stay the same. So, therefore, acceleration will remain the same no matter how big or small the object is. That would mean that since acceleration is a measure of how fast objects speed up, and our starting speed will always be 0 if we drop it perfectly, that is, that would mean that the objects will have the same speed throughout. If they travel at the same speed all the way through, that means they will theoretically reach the ground at the same time. Well, that is if we ignore air resistance. Anyways.
Basically, in short, most of the time objects will fall towards the Earth at roughly the same time. Unless, as Kevin mentioned, the effect of air resistance on one object is much larger than the other. Just like in the case of the rock and the paper compared to the rock and the pencil. More air is pushing on the paper, which is why it falls slower, which is exactly how a parachute works, like we mentioned before.
Exactly. And I guess that's the end of the explanation.
If you have a doubt, please make sure to send us the questions. If you really do have any, we can answer it for you. Anyway, in that case, we'll just end it here. Thank you for watching.
Yes.
Bonus stage.
Small pencils.
That's pretty. Okay, we can use that.
We can use
And
this.
this will be part of the video as well.
Yes. Oh, will it?
Yeah.
Oh, then we can use this paper because it's fairly useless.
I mean, scrap paper.
It's just scrap, yes. Reuse some math stuff.
Yeah. Okay.
And then what
Rock.
else?
A rock.
A rock we can find outside.
Okay, we'll use this. Hey, now I'm gonna have to get that rock. I think that was a bad idea. Hey, but okay, give me that.
Wait, what the heck? Who am I calling?
I got it. Oh my god, this thing's heavy. I got it. Wait. Oh god. At least you got the rock.
Where did you throw the rock?
There on the floor.
Oh.
Okay, well. Where's the stand?
We will get the stand. You just have to tell them what we're doing first.
I told you we're dropping a bunch of stuff.
Okay.
Should we drop it in the water?
Then we lose the chance to reuse it. Oh, you might have to get the other part that's important for this. I'll go and get that while you take this. No, it doesn't.
Yes.
No, it's
Yes, it works.
We're gonna have to voice over.
No, we who uses voiceover? Let's go. Off, please. There we go. Okay.